organizing this nice event, and thank you to the committee for accepting our paper. So this is joint work with Tímea Csahók, Mickaël Montessinos, and Gergely Zábrádi. Okay. This well.
Every time, let's make it then you did. Yes, click on the background and just click once. Yeah.
Okay. Okay, so this talk will be about algebras. So what's a finite dimensional algebra? So an algebra is just a K vector space, which is also a ring. And it's finite dimensional if it's finite dimensional as a K vector space. And so you want to somehow understand the structure of an algebra, and there are various components you have to study here. So first there's the radical, which is the intersection of all the maximal ideals, or in this particular case, it's also the collection of strongly important elements. So that's somehow like the bad part of the algebra. So if you factor out with it, because that's a two-sided ideal, then you get something quite nice. So simple algebra is just an algebra with no non-trivial two-sided ideals. And if you factor out with the radical, you get something which is a semi-simple algebra, and it's actually a direct sum of simple algebras. And the simple algebra also has like a particular structure. It's always a full matrix algebra over some division ring. So from a computational perspective, we want to somehow compute the structure of an algebra. But how is our algebra given? So that's not quite obvious. There are various ways of representing an algebra. There's a particular simple way that you'll be mostly using here. Namely, one is given a basis, a K basis of the algebra, and the multiplication table. So I'm given two basis elements, Bi, Bj. If I multiply them, that's just a linear combination of all the basis elements, and those coefficients are sometimes called structure constants, and this is what is given to me. Alternatively, you can also think of this as like the regular representation of the algebra, meaning that you represent every element by an n times n matrix, because an element multiplication by an element from the left is just a linear transformation. Okay, so now you want to compute the structure of the algebra, so you want to compute all those components I mentioned before. So first, you want to compute its radical. That is quite easy. So if the characteristic is 0, then it's just linear algebra. When it's characteristic p, it's a little bit more complicated, but anyhow, there's a polynomial time algorithm for doing that. And then you want to compute, okay, you factor out the radical, you want to compute the semi-simple components. I mean, you want to decompose it as a direct sum of simple algebras. That's also quite well understood. So this basically reduces to just factoring over over the polynomial ring K. And interestingly, somehow the hardest part is really understanding these simple components. So when it's given a simple algebra, and you want to find, you want to represent it as a full matrix algebra over some division algebra. So this is a concept that probably everyone knows. I will try to briefly recall it though. So if you want to understand simple algebras, it makes sense to like fix the center. So the center of a simple algebra is always a field. So let's say it's a field K. And then you can study the notion of a central simple K algebra, which just means that its center is K. And central simple K algebras, you want to understand them over a field. There's the notion of the Brauer group, which helps you do that. So namely, you study equivalence classes of central simple algebras, and you call two classes equivalent. So everything is just a matrix algebra over a division algebra, and if that division algebra is the same, then you call two things, two CSAs equivalent, Brauer equivalent. And on that, you have a nice group structure, namely just using the tensor product. The trivial class is just M and K. And then inverse is just this opposite relation where you take the algebra and reverse multiplication. And the Brauer group has a nice cohomological interpretation, which we'll be using implicitly here. So it's the second Galois cohomology group of GK, where G is the absolute Galois group and K is the separate group closure of K. And in this context, actually, if one looks at this isomorphism problem, so suppose one is given two central simple algebras, and I want to compute an isomorphism between them, you can actually reduce it to just computing an isomorphism between some full matrix algebra over the field and another object, which is just the tensor A with the opposite algebra of B. So really what one mostly cares about is just when it's given some algebra and we want to compute an isomorphism between M and K. Okay, so you would, okay, at this point, it's not quite clear why this paper is interesting to the ANS community. This looks like more like computational algebra. But interestingly, this last problem I mentioned has applications throughout number theory in various aspects. So the first, probably the simplest application is norm equations. So norm equation, yeah, we have in this case, I will restrict to cyclic extensions. So I have a cyclic Galois extension L over K of global fields, say, and Galois group is generated by some sigma, and I am given an element gamma in the smaller field. And I want to find an element in L whose norm is exactly gamma, or show that it doesn't exist. And this is exactly the same problem as looking at the cyclic algebra. And so the cyclic algebra is isomorphic to M and K if and only if this gamma is in the image of the norm map. And this correspondence is also quite explicit. So if you can find this isomorphism, you can solve the norm equation. So like the simplest case that probably everyone has already encountered is like when you're given a quaternion algebra, finding a zero divisor in a quaternion algebra is exactly the same problem as finding points and conics. Then a second very interesting application, which is, hopefully I didn't miss any of the answers here. Okay, so it's so there was a talk on Tuesday on 2 descent, but in general on n descent, there is a paper by Cremona, Fisher, O'Neill, Simon, and Stoll, which describes a connection of this problem to explicit n descent on the elliptic curves, which is a method for computing generators of these weak model Weil groups, which helps you to find actual generators of the big model Weil group. And the key step in that algorithm revolves around a notion called the obstruction algebra, which somehow measures failures of the local global principle. And if you can find, so one step is trivializing this obstruction algebra, which is just finding an explicit isomorphism between. So the K there is actually Q. So in that case, it's just a rational number. So finding an explicit isomorphism between M and Q and this obstruction algebra. And another application is parameterizing Savary-Brauer varieties. So Savary-Brauer varieties also have this property that they have a rational point if and only if some central simple algebra is split. And finally, factoring Ore polynomials, which are just polynomials over a field K, but they're non-commutative polynomials. So the K doesn't commute with the variable. Actually, the conjugating with the variable induces an automorphism on K, which is interesting on its own, but also has applications supporting theory. Okay, so hopefully I've convinced you that this is a problem worth studying. And I will give some quick remarks before recalling the basic literature here, because I will be using these notions quite a lot throughout the talk. So actually, finding an explicit isomorphism between M and K and your algebra given by structure constants is equivalent to finding a rank 1 element in your algebra. So you would think that this is nonsense, because how do I know that my matrix has rank 1 if I don't have an explicit isomorphism? But you can do that because there's a notion of rank which is independent of this isomorphism. You can take the left ideal generated by that element, and the dimension over K tells you the rank. So you can compute the rank of an element easily without actually computing its matrix representation. Finally, it's actually also somehow enough to find a zero divisor in your algebra. Oh yeah, I didn't tell you why it's actually enough to compute a rank 1 element. So if you find a rank 1 element, you can look at the left ideal it generates, and you can look at its action by the algebra multiplication from the left, and that actually reveals every element as an n times n matrix. And in general, when you just find a zero divisor, which might have bigger rank, you can reduce the problem to a smaller instance by computing an idempotent of rank K, and then this easy observation that EA is just isomorphic to MKK tells you that you can reduce to a smaller instance. So from now on, I will basically interchangeably say finding isomorphisms, finding rank 1 elements, and zero divisors. And somehow this already tells you the hardness of the problem. So So zero divisors, they're like a Zariski closed set in the big algebra, because you can look at this just if you look at it from a matrix point of view, it means that their determinant is zero. Okay, so what was known before this work? So one you can consider, so in this talk I will be focusing on global fields. So in that case, the easiest case you can consider is that your algebra is isomorphic to M2Q. And unfortunately, the first result is like a negative result here. This problem is at least as hard as factoring. But it's not really a big deal, because in most cases, you don't really want these instances for huge numbers. So is it exactly as hard as factoring? And the answer is yes, it's equivalent to factoring. And since this is a fundamental problem, because this is exactly the same problem as finding conics over the finding rational points on conics, there have been various works providing algorithms for this result. And then you can consider the natural generalization. Your A is isomorphic to M and K, where K is some number field. And there is an algorithm by Ivanov, Ronyai, and Csahók, which is based on an idea of Tom Fisher. And that algorithm solves the problem in polynomial time, but the polynomial is just in the size of the structure constant. So the algorithm is exponential in n, it's exponential in the degree of the number field, and is exponential in the discriminant of the number field. So it actually only works for like a finite number of cases. The reason for that is that what it does, it computes a maximum order and shows that there is a maximum order is a lattice. So you can show that it has like a small norm element, which has rank 1, and then you just scan through all the elements of small norm, and this is an expensive step. Then when A is isomorphic to M and K is a rational function field, FQT, then surprisingly, this algorithm runs in polynomial time even in n. The reason being is that there is non-Archimedean valuations are nicer than Archimedean ones. But this algorithm doesn't generalize for function fields of higher genus. So, and there are two more cases which are known, which are very close to each other. So the case where A is isomorphic to M to L, and L is either a quadratic extension of FQT or Q. And I think all of these algorithms rely on solving quadratic forms over the smaller field, either FQT or Q. So in this work, we'll generalize this in probably a more conceptual way, and apply it to a setting that was not quite known before. So namely, when one is given two quaternion algebras over quadratic global fields, and they are isomorphic, and I want to find an isomorphism between them. And you could ask, okay, why isn't this covered by the results I just mentioned? So you can still do this tensor product trick, but then you have to trivialize an algebra which is isomorphic to M4 over a quadratic extension, and we don't really have algorithms for that are efficient also in the size of the discriminant. Plus, we also handle the characteristic 2 case, which was not really handled before. And so the key here, I think, is a method that hasn't been used before, and I think it's interesting, and hopefully we'll have other applications, is namely to use a form of Galois descent here. So what does this mean? So suppose you're given an algebra which is isomorphic to M and K is a big number field, or it's not Q or FQT. Then, okay, so the algorithms become really bad because this lattice is huge. But maybe you could do like a first step and computing a smaller central simple algebra, which is a subalgebra over a smaller field in the bigger field, and ignore all the other information that you have in the algebra and just work in this smaller thing. And this is exactly what Galois descent would actually do. And the way to achieve Galois descent is through a technique which is called the Corestriction of central simple algebras. So I mentioned that there is this cohomological interpretation of the Brauer group. So it means that you have restriction, you have corestriction on the cohomology side. But you somehow want this to be more explicit, and restriction is pretty simple. So restriction corresponds to just extension of scalars. So if you have a central simple K algebra, you can create a central simple L algebra by just tensoring it out. But the other way around is not quite simple. So if you have a central simple L algebra, how do you create a central simple K algebra corresponding to this Corestriction map? And I think this was not immediately known to Brauer, so this was developed maybe in the 70s or something. So I will just probably I'm not great on time, so I will just briefly explain the main idea here. So the idea is to increase the dimension. So this Corestriction will be a central simple K algebra which lives in A sigma, which is a K subalgebra of A sigma tensored with A, and A sigma is just like a conjugate algebra of A, where you conjugate every structure constant, and you use some nice certain invariants. But anyway, the main takeaway here is that this is a central simple K algebra, but has much bigger dimensions than the original algebra that I started with. So since it's not a subalgebra of A, or it has much bigger dimension, it cannot be directly used for Galois descent. And the way to circumvent that is to use something which are called involutions. So an involution on a central simple algebra is just a linear map which has order 2. So if you apply it twice, you get back the identity, and it reverses multiplication. So and so if you restrict it onto the center, then it must be an automorphism of degree at most 2. So if it's a degree 1, so it means it leaves the center intact, then it's an involution of the first kind. If it's a non-trivial automorphism of degree 2, then it's an involution of the second kind. So to see this, and with matrices, is essentially just involution of the first kind on matrices is just the transpose, and then second kind is the adjoint. So you take the transpose and you apply conjugation. And there is a theorem, I don't know by whom, probably Albert, that if you have a separable quadratic extension, and you have a central simple L algebra, then this central simple L algebra possesses an involution of the second kind, if and only if this Corestriction is split, meaning the Corestriction is just a full matrix algebra. And interestingly, this theorem is, the proof of this theorem is quite explicit. Namely, if you somehow understand the structure, you trivialize the smaller central simple algebra, then you can actually compute the involution as well. The way is this formula, basically, that if you find a right ideal of the Corestriction that satisfies that property, then you can explicitly construct an involution of the second kind. And most of the time, like a maximal right ideal should do the trick, unless those two things have some non-trivial intersection. But if they do, then you automatically found the zero divisor of A. So essentially, it's just finding a maximal right ideal, which is exactly the same problem as finding a rank 1 element. Because if you have an idempotent of rank 1, then 1 minus E will be of rank n minus 1. Okay, so I'm ready to describe the main algorithm. So again, the starting point is 2 quaternion algebras over a quadratic extension. So as I mentioned at the beginning, so finding an explicit isomorphism then is the same as trivializing A tensor B up. And that gives me an algebra isomorphic M4 L, or I don't know what I call it L, M4L. And so there were no previous algorithms for that, but this is not like a generic structure constant representation. You have much more here. You have the representation, so it's represented as a tensor product of 2 quaternion algebras, and you can leverage that by computing an involution of the first kind on this. Because if you so quaternion algebras come equipped with a involution of the first kind. It's just conjugation, and you can extend that to the tensor product. So this tensor product immediately comes equipped with an involution of the first kind. Then what you do is you compute an involution of the second kind using the method described before. And you can do that because this Corestriction is an object over the smaller field. Okay, so you have an involution of the first kind and an involution of the second kind. What you do is you can compose them. And an involution reverses multiplication. But if you take two involutions and they reverse multiplication twice, and then the composition is going to be a K-algebra map, it keeps multiplication, hence you can take invariant elements under that. And the invariants are now actually a Galois descent here, meaning they will be a central simple K subalgebra C, such that if you tensor with L, you get back the big thing. And okay, but this might not be super useful, because if this was like a division algebra, then it's completely useless, because then every element is invertible and you won't find any zero divisors there. But the good thing here is that since L is a quadratic extension and the C is a degree 4 thing, it means that it's split by a quadratic extension, so it cannot be a division algebra. So there are only two choices here that this can be. It's either M4K or it's either M2D. And so the main thing here is that, again, these are smaller objects over K, and there exist algorithms for finding zero divisors there. A little bit of a reinterpretation of this method is like not with actually an algorithm, but like reductions, because essentially there are various components you have to see. And if those exist, then you can apply it for other cases as well, not just the cases mentioned here. So there are certain subroutines that we are actually using here. So one subroutine is when B is isomorphic to M2L. This was mentioned on the slide. Another subroutine is the case of B is isomorphic to M4K. It's also mentioned on the slide. So here actually, so to recall, so K is just a Q or FQT, and L is a quadratic extension. Then what was not quite mentioned is how to find zero divisors in M2D, where D is a quaternion algebra over K. Maybe I said 2 sentences about this. So the idea there is actually to compute Hasse invariants of this. And then if you know the Hasse invariants, in this case, they're pretty simple to do. You can reconstruct D using also not complicated methods. And if you know D, then you can, from that, it's quite easy to actually to find zero divisors there. And finally, this is the Corestriction step. So you need to be able to trivialize M16 K. So as you can see, this is probably going to be the most expensive step. So we also implemented our algorithm. So this algorithm works for, so the nice feature of this is it doesn't really treat FQT or Q in a different manner. It's a framework that works for all of them. But for implementation choices, we chose to implement the FQT version. For the reason being is that for example, you have to find rank 1 elements in M16K, and that is technically polynomial time using the Vilnius algorithm, but the constant is huge. But there shouldn't be like, so the MNF, so the FQT version shouldn't have been like a big problem. But there was one caveat which so I would like to draw attention to the community regarding this. So there is one step in the algorithm which computes a maximum order in this central simple algebra. And that is a well-known polynomial time algorithm. The issue is that it's polynomial time, but with a huge exponent in the input, probably like n to the 12 or something like that. So it's completely not practical, unfortunately. And so as you've seen, so we need to use it in degree 16. So the dimension is 256, and that is already too big for the algorithm to handle. So we try to do some optimizations here, because again, we are not like in a generic scenario that we're just given M16K as a collection of structure constants. It comes from a Corestriction that comes from the tensor product of quaternion algebras. So for example, if we restrict ourselves to quaternion algebras with not too many ramification places, then it's you can compute a maximum order at least in M4L, and then that somehow translates to a rather big order in this Corestriction, because this maximum order finding algorithms, they're all the same. You compute some starting order and then start to increase them locally. And if they have many places which they aren't locally maximal at, then the algorithm is more expensive. So we will try to salvage these ideas, but unfortunately the computation was still not quite feasible to be carried out on a laptop. Maybe I've seen so many talks with like huge clusters here. Maybe we should have tried that one. But in the end, I think it all boils down to the fact that people should actually, I encourage people to work on having faster algorithms for computing maximum orders, because I suppose many people didn't think it's worth working on that because there is already a polynomial time algorithm. But it would really help this algorithm a lot. So we tested all the other components seem to be fine. Then another open problem, how much time do I have? Okay, that's great. So we'll quickly mention just one or two open problems here. So I really hope that this Galois descent approach will have more interesting applications. So here the issue was that somehow you could only do this with like a double twist. It would be nice to have it more directly and not go to higher extensions, but to much bigger algebras. And then would also be nice to not just do it for quadratic extensions, but maybe generic cyclic extensions. And that would be interesting, for example, in the case of conics, because if you have like a conic over an odd extension, and if you find, or alternatively, you have a quaternion algebra defined over an odd extension, then finding a Galois descent there immediately gives you just M2Q. Because again, the splitting field has to be divisible by 2. Okay, so I probably stop here and thank you for your attention.